this computer. All right. Good morning, everybody. This is Organic Chemistry 2330. I'm sorry, 2341, section 253, 8 a.m. on Tuesday, Thursday. So today we're going to continue on with our learning of organic chemistry. Last two lectures were all about what bonds are, what hybridization is, and stuff like that. Look for, in the next week or two, follow-on videos, uninterrupted short videos with short topics that will have those individual topics laid out. And so if you're having trouble with like hybridization, there'll be just a hybridization slide or a file. And if you're troubled with geometry, there'll be just a geometry thing. So start looking for those as they appear in our there's an organic chemistry playlist that'll be connected to your Canvas site. Okay. Now, to complement what we're going to start today, which is Module 2 Nomenclature, if you go to Canvas and look at resources, there is a nomenclature review. And it's basically all the rules. It's taken from all these different sources together, but it's all the rules we're going to start going over today. And they're all in one place. So it makes it easy for you to go back to it. Now, that being said, nomenclature is the next most important part of organic chemistry, okay? Because when we have clear, concise nomenclature, that means whenever I write down a chemical name, you can then draw that chemical with no ambiguity at all. So there is a precise way to name every single compound, but don't worry, all we have to do is follow the process. If we follow the process, you'll get to the correct answer most of the time. Okay, so what I'm going to do is I'm going to walk you through nomenclature, and we're going to start first with functional groups and priorities. Okay, so now I'm going to share my screen with you via cable. There we go. And my iPad is now sharing properly like it always did before until I updated. All right, I'm moving the gallery view onto this side here. I still have my chat and my participants here. So every once in a while I'll pause and I'm letting somebody in from the room here. So let me go ahead and start with this Module 2 nomenclature. Okay, so in general, we are going to get through this by understanding the structural difference between the different hydrocarbons. And these are things with only single bonds, things with double bonds, and things with triple bonds between carbons. When we do this, we will also talk about the different types of functional groups. I said when we were bonding, we have different types of bonds. We have polar bonds and non-polar bonds. And the polar bonds are the ones that are going to do more chemistry. And we had single bonds, sigma bonds, which were not very reactive, but double bonds and triple bonds are more reactive. Okay, so because of that, they have different names because they have different reactivities. And we're going to understand that. And then we're going to go through the IUPAC rules, which is the International Union of Pure and Applied Chemistry. Haha, got that right the first time. And we're going to use their rules to make sure that every time we name a structure that everybody in the class can draw it just by looking at the name, or everybody can get that name just by looking at the structure. And all we have to do is follow a certain number of steps, and we will get to this every single time. All right, moving along. Okay, so the first thing I want to do is I want to talk about understanding the parts of the name. Okay, so there is several parts of a chemical name. If we break it down into something like, a very long word like, flossy posse nihilipilificationism, which is one of the longest words I know, there's actually lots of infixes, prefixes, and suffixes. And so I want to define those and tell you how we're going to use them in this chemistry. A prefix tells all of the lower priority groups attached to the parent. Okay, so at some point we're going to say this is our parent, this is the longest number of carbon chains, and our compound is being named for that. Okay, so we're going to have all the things attached to it and the number of atoms, carbon atoms, in that parent chain. So that's the first thing we're going to do. The second thing we're going to do is we're going to have what we call an infix. An infix is just two letters, but it tells us that if we have a carbon-carbon single bond, carbon-carbon double bond, or carbon-carbon triple bond. Okay. And then the last thing at the end of the thing actually names the class of the compound, and we always name it for its highest priority. So different functional groups have different reactivities, and therefore there are higher priority as we go into higher types of functional groups. Okay, now we're not going to get a lot of these functional groups until the second half of this. However, it's good to know the names so that we can look forward, and we're going to be using about half of these functional groups this semester and then the rest of them next semester. So we're going to look at functional groups and how they name our compounds. Okay, got that? All right, so yes, this is a very busy slide. So the first thing you should do is you should go to Canvas and download the nomenclature review and functional groups you should know. Okay, so the functional groups you should know are listed there, and they are given, it's basically these things here laid out. Now, the cool thing about this is that in this example, what we have is what we call a generalized scheme. Okay, so in this right here, any long chain hydrocarbon can be truncated into an R. Okay, that just means any hydrocarbon. It can be any hydrocarbon at all, and X typically means any halogen. Okay, so that's the generalized structure of it. So get used to the idea that R is just could be anything, but we can't name specifics until we know exactly how many carbons there are. Okay, so that R could be anything. But the next most important thing is what the functional group is here. And in this case here, we have a halogen, and it could be chlorine, bromine, or iodine, and it's attached to an alkyl group. And so that's going to be given the name alkyl halide. So I'm not going to go through all these right now. I'm going to go through all these as we go into other things, but I wanted to show you that this is how we identify them. So the functional groups we're going to need to go we're going to need to go what an alkyl is. That's a carbon chain with only carbon-carbon single bonds. If there's one or more double bonds in the carbon-carbon double bonds in this, we now call it an alkene. Okay, it has an E in it instead of the A. Alkane has an A, alkene has an E, and I'll go into detail. And then if we have a triple bond, it's an alkyne. Okay, so by changing that nature of the carbon, this is what the infix is going to be. Okay, the alkane, alkene, and alkyne. But then we have other functional groups. When the functional group changes the name of a compound, that gives it a level of priority. Okay, so things like alcohols will change the name of the group. Ethers are actually substituents. Thiols change the name of the group. And so then we can get up to these very fancy carboxylic acid derivatives right here, and we'll see that they change the name of the thing, and they have different priorities. All right, let's talk about priority. Okay, so when we're talking about does the compound change the name? Okay, only if you are something like an alkene or an alkyne do you start to change the name. If you have any halogen, alkyl group, or alkoxy group, right here, or an aryl or a nitro group, you don't actually change the name. It's just a substituent. Okay. Once you change the double bond, triple bond, that actually does change the substituent. And then as we go up for functional groups, we go up into nitrogen-containing functional groups, which could be amines, sulfur-containing functional groups, oxygen-containing functional groups, and then we start adding carbonyl compounds. We have a variety of these that we're going to look at. And as you go to that more and more complex, the more and more reactive, you get to higher and higher priority. What does that mean? Okay, that means if you have any one of these functional groups on your compound's going to be named for that. And any of these other groups here are going to be in the prefix. They're going to be substituents. Okay, so what you have to do is look for the highest priority functional group, and that names the compound. Everything else is a substituent, and it is found in the prefix. Okay, So that's just a review of where we're going with this. I'm going to go and start to get to the specifics on how we do this, okay? So I'm going to go step by step, and so that we will make sure we understand all the rules and the order of the rules. But my first rule is always to figure out what the highest priority functional group is. Okay, so let's move on to hydrocarbons. All right, so this is where we're going to start. These are the simplest organic compounds. These compounds only contain carbon and hydrogen. Okay, so if there are only carbon-carbon single bonds and carbon-hydrogen bonds in the compound, we call that an alkane. Alkane. Oops. Alkane. And when we look at our stick structure, they're going to look like this, where all the lines are the bonds between two carbons, and the hydrogens are assumed. Okay, so anytime you see a long zigzag chain like this, even if it all shaped funny like that, it is an alkane if it does not have any double bonds or triple bonds. Once we add a double bond anywhere in the chain, that changes the name and it becomes an alkene. Okay, now alkenes are also hydrocarbons, but you just end up having a double bond somewhere on your chain. Okay, and knowing where that double bond is important, and we need to pay attention to that. Now, if you have at least one triple bond in your compound, you have gone up to an alkyne. Okay, and so in a stick drawing, that'd be something like this. I guess it wouldn't be bent like that, actually. Let's redraw that. Anything like, so this has 3 triple bonds in it, and it's still an alkyne because it has at least one in there, okay? Now, the next thing that we have is what we call aromatic compounds, okay? Aromatic compounds are compounds that contain, a ring of alternating single and double bonds. The most common one is this 6-membered ring here. And they have a different reactivity compared to all the aliphatic hydrocarbons. And we're only going to use these on rare occasions as reagents. Right now, we're going to take, and we're going to do an entire chapter on aromatics next semester. Okay, but I just wanted to show you that those are there, and those count as pendants most of the time. Okay, so let's talk about alkanes. Alkanes, the key here is this ANE. That AN tells you that you have only sigma bonds. Okay, there's no pi bonds, and its general formula is going to be carbons having any number of carbons, and you can always figure out how many hydrogens there are by taking 2 times the number of carbons and add 2 on the end. So if you think about it here, you have 2 hydrogens, 2 hydrogens, 2 hydrogens here, and then you have to tack 2 on the end. Okay, so this is an alkane. Okay, now we give the names to these by how many carbons are in these chains. So in this case here, we have 1, 2, 3 carbons. And what we're going to learn is there's a special name for 3 carbons in a cis, and that prefix is called prop. Prop means 3, and I'll go through all of the numbers and you will have to know these and memorize these. After a while, they become very systematic, but so 3 is prop, and so we have no double bonds, so we have ANE at the end, propane. 4 carbons would be bute, 5 carbons would be pent, okay? So it's simple enough to name the number of carbons plus the fact that we have only sigma bonds that's how we name our compounds, okay? So when we have these linear chains, we want to think about the longest chain of continuous uninterrupted hydrocarbons right here. We name them dependent on that name. And so these are the ones you're gonna have to remember. The first one starts out with, if it was just 1 carbon, it's meth. And so if it was a hydrocarbon with just 1 carbon, we call it methane. Then we go to eth, that's 2 carbons, ethane. Prop, 3 carbons, bute, 4 carbons, pent. See, now these start getting nice and familiar. Hex, hepta, octanana deca. So that's, 6, 7, 8, 9 right here. And then we have un meaning 1 deca, so 1 plus 10, 11. Do meaning 2 deca, 12. Trideca, tetradeca, pentadeca, until we get up to 20, which is icos. Okay. Don't worry about these. I only want you to know up to icosane. Okay. So these are things you will have to remember, and they are associated with a number of carbons here. The hardest ones are these right here and icosane, because they're not as familiar. Okay. So when we're looking for hydrocarbons, we're looking for the longest chain. That longest chain is what we call the parent chain. That's pretty important because that's going to be the name that we use in our compound. That's going to be in that prefix. Okay. All right. So why did I say the longest continuous chain? Well, only if you have a long chain of carbons, it's very likely to have branches coming off of short chains of other carbons. I'm not sure. That's an interesting question. There's a question in the chat about, would 21 be un icosane? And it makes sense that it would be, but I'm really not sure. I would have to look it up. Great question, though. Okay, so let's get back to that. So we have this long chain. The longest continuous chain is what we call the parent chain, or you can consider it the trunk right here. And then any other shorter group of carbons coming off of that chain are considered branches. So what I mean by that is, if we have this chain right here is 20 carbons long, and then this branch has 2 or 3 carbons on it, it's a branch. But we have to make sure that the longest chain is actually the one we've measured by counting out the number of carbons total on there. And so you have to count sometimes twice back and forth across the chain to make sure you have the parent chain. Okay, so if you have these trunks on here, you name this for here, and now all of these branches, smaller branches, are going to be named individually and put as prefixes to your main polymer. Your main chain. Okay, so these substituents are derived from alkanes, but are different than other alkanes because they lack one hydrogen, because they had to attach to our main chain. So, for example, this right here would have 2 carbons on it. So that would make it ethane. But because it's a branch, it has 1 carbon missing, and we actually call it something else. We end up calling it an ethyl, because it's a substituent. Anytime you see the YL on there, it's a hydrocarbon chain with that many carbons on it, but it's a substituent on a larger chain. Okay. Now, these substituents can be unbranched, meaning also straight chains, or branched. Okay. So if they are branched, they would have additional substituents on those chains. And we have different names for common branched systems, and those are things you'll also have to remember. And when we start adding those to there, we need to make sure that we base the number of carbons on the longest continuous chain of the substituent, and then start adding in the different things that are on that backbone. Now, let me do one thing here. I want to prove to you that our parent chain is the one on the bottom in black by counting our carbons. So if we count from one side to the other, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now, if we counted from this way up this chain, we'd only end up with 8. If we counted this way, we would only end up with 6. If we counted this way, we'd only end up with 6. And likewise, if we go this way, it's 8, 8, and 6, meaning that the longest continuous chain is this 9 chain. Okay, so that's why I said sometimes you got to number it a couple different ways to make sure that you have the longest parent chain. Okay, all right. So now let's get back to the substituents. When we have those substituents, you name it for the number of carbons you have, but you actually drop the ANE, which is the suffix that told us it was a hydrocarbon, and we put the YL on it. The YL tells us that we have a substituent that is a hydrocarbon. So in this case here, this would be the ethyl group because it has 2 carbons. And this is a methyl group because it has 1 carbon. Okay, so it's as simple as taking the number of carbons you have, drop the ANE at the end, and add the YL. That tells you you're missing 1 hydrogen and it's attached to a parent chain. So what if you have a branched chain? Okay, well, then you have to pay attention to, is it a common branch chain or is it something else? Okay, so the carbon attached directly to the parent chain is assigned number 1, and the longest chain of those substituents is then numbered from there. So our parent chain right here, we number from the ends, okay? Substituents, we number from where it's connected to that parent chain, okay? So we connect from that parent chain, and so we have the longest available is 1, 2, 3, 4. If we count it this way, we'd only have 3. So that means our longest chain is these 4 carbons here, and it has a substituent. Okay, so now that we know what our longest chain is, we know that this is going to be 4 carbons, which is going to be butyl. So we're going to have butyl as one of our names, but we have another substituent on that substituent. So we have to name that as well. So the way we're going to name that is we're going to say, oh, well, this methyl group, this other substituent is on the number 2 carbon. And so our substituent is actually going to end up being 2-methyl-butyl onto whatever our parent chain is. And we'll do that rule again, but just to give you a heads up. Okay, now it's important to understand the different classifications of carbons, okay? So because number 1, they have different reactivity, number 2, they have a different number of things attached to them, and we need to keep track of that. So a carbon with only 1 other carbon attached to it is called a primary. Okay, back up. A carbon with no other carbons attached to it is called a methyl. And because that's just the 1 carbon with hydrogens on it right here. So that's the methane. Okay. But if there's 1 other carbon attached to it, and the first simplest one of that would be ethane. Ethane is going to be called a primary. Okay. Now, if there are 2 carbons attached to it, see 1 on this side and 1 on that side, it's a secondary. Okay. So this is simple. This one's going to be tertiary because there's 1, 2, 3 things attached to it. And of course, this one's going to be quaternary, which is have 4 other carbons attached to it. So it's important to know because that's going to tell us a little bit about what the reactivity is. And they're also going to be very important when we start looking at reaction mechanisms. Whether it's a primary, a secondary, a tertiary, or a quaternary carbon tells us whether or not they're going to react. So it's good to know that classification. Okay, so now when we have substituents, there's some common names, and yes, you will have to remember these. Some of them are simple because they follow the UPAC name, but some of them have different names. Okay, so I'm going to go ahead and blow that up right there. So if they're just straight chain hydrocarbons, they're easy. You use the UPAC name for the number of carbons and add the YL. So in this case, we had 3 carbons, so that's propyl. 4 carbons and 5 carbons. So those are simple, straight chains are simple. However, when they're branched, they have common names as well as IUPAC names. Okay, so let's pull up the first of these. When we have the shortest chain we can have branched is a compound known as isopropyl. Okay, now it's an isomer of propyl because we have 1, 2, 3 carbons, but it's not a straight chain. And notice that it's attached and that center carbon. Okay, that differentiates propyl from isopropyl. Okay, now just like in the previous slide, When we name the substituent on this IUPAC wise, we have 1 carbon, 2 carbons as our longest chain, and we have 1 carbon left over, and it's attached to that number 1 carbon. So the IUPAC name would be 1-methyl ethyl as that substituent attached to whatever the parent is. Okay. So think about it as isomer of propyl, and that's how we think of isopropyl. The next thing we have is what we call the next is the 4 carbon chains. And we have a couple different varieties available to us here. The first one here is we call the isobutyl. Now notice the isobutyl looks a little bit like the isopropyl from this side over, but we've added 1 more carbon to it. Okay, so that's how we get isobutyl. And if we were to number these from where the parent attaches, remember the parent attaches here, so this is going to be 1 carbon, 2 carbon, 3 carbon. So that gives us this as our 2-methyl propyl for our IUPAC name. Okay, so notice that this is on the 2 carbon here, that methyl group here. That's what differentiates itself from this other one here. The next one down is what we call sec-butyl, okay? And if you think about it, that makes this one right here, the parent is actually attached to a secondary carbon. Notice this is a primary carbon up here. This is a secondary carbon right here. So that's why we call it sec-butyl, okay? But if we look at the IUPAC name, we still have 1, 2, 3 right here as our longest chain, but we have 4 carbons. So that gives us our propyl for our longest main chain. And we have 1 methyl group here, and it's attached to that number 1 carbon. So it's 1-methyl propyl, or sec-butyl, secondary carbon attached to the parent chain. Okay. Now, the only other isomer available to us is what we call T-butyl. And in T-butyl, we have a tertiary carbon attached to the parent chain, but we still have 1, 2, 3, 4 carbons. So we have butyl, but it's tertiarily attached to the parent chain. However, if we were to go with the IUPAC naming, we would have 1 and 2, and that would give us 2 methyl groups on that 1 carbon, which gives us the name 1,1-methyl ethyl as our substituent. Okay. Do you see how things build slowly and they are very precise about where things are attached? Okay. So the other common groups that you need to know are the last 2 here are the isopentyl or isoamyl, which again, iso has this little group on the side here, so it looks familiar, but it has 2 more carbons added onto it. And so that's how we get to the isopentyl. And then the neopentyl is where we have the tertiary butyl group on here with 1 more carbon. Okay. So those are the common branch names you need to know: isopropyl, isobutyl, sec-butyl, tert-butyl, isopentyl, and neopentyl. Okay, so that way, but if you don't remember those, you can always write in the IUPAC name. All right, questions on common names. We don't count the carbon on the parent end. No, because the carbon on the parent counts for the parent. So we're just talking about the 1 carbon off of, we're starting with the first carbon off of the parent chain. So yes, that is correct. You do not, the parent chain is independent and names the compound. These are just the substituents. All right. All right. So when we name branch type alkanes, we're going to, number 1, identify the parent chain. Well, the first thing we actually did, we identified that there were no other functional groups. Okay. So we identified it as a branched alkane. Okay. So now we need to identify the parent chain. So we need to find the longest continuous set of carbons that is not ambiguous. The second thing we need to do is we need to identify the substituents. Okay. Now, because we can number the compound from either way, we actually have to assign a location to each substituent. And we have a specific rule for that, and I'll get into that. Then you can name the compound, and in the prefix, you're going to list the substituents in alphabetical order, also assigning them with the number of the carbon that they're attached to. Okay, so let's go through all these rules real quick. real slow, just to make sure we have it. Okay, so we need to make sure we number the chains to make sure we know we have the longest possible chain. For example, if we were to take this compound here and number from this side and go 1, 2, 3, okay, 3 can't be our parent chain. 1, 2, 3, 4, 5, that can't be our parent chain. 5 here, 6, 7. I mean 6. 1, 2, yeah. So that means that it has 6 will be our longest chain. So now that we've convinced ourselves that 6 is our longest chain, now we have to number it correctly. Okay, now to number it correctly, well, sorry, step 2, identify your substituents. In this case, we have a methyl group as a substituent, a methyl group as a substituent, and a methyl group as a substituent. Okay, so that's rule 2. Find the longest chain and then find all of the substituents. Okay. Now, how do we number it? That's the next rule. The next rule is we number it where we want to get the first substituent encountered at the lowest number. It doesn't matter alphabetical order yet. It's just whichever one is first. And so if we numbered from this direction here, our first number would be 3. If we numbered from this direction here, our first substituent would be number 2. Okay, so we always number the parent chain to get the substituent on the lowest number possible. Okay, and notice it's the first lowest number because we have 2 4s here and we have 2 3s here. So all that matters is that first lowest number. Okay, so now that we have that first lowest number, so now we know that our substituents are on the 2 carbon and we have 2 substituents on the 4 carbons. So now we have to identify our substituents. Okay, now cool thing is if they're all the same substituent, like a methyl group or an ethyl group or a propyl group, you can actually designate that by saying that it's a dimethyl, trimethyl, tetramethyl, etc. By adding a di in front of it, it means you have 2 of them, 3 of them, 4 of them. Okay, so that simplifies the name. However, you still have to identify each carbon that those methyl groups are on. So notice here we have, come on, there we go. Right here in our name, we have the methyl group because that's our substituent. We have 3 of them, so we get to say tri. And our longest chain was 6, so we have hexane. So this is our parent chain, hexane, hex, 6, ane, hydrocarbon. We have 3 substituents on there, so it's the trimethyl. Okay, but again, the nomenclature has to be very specific. We have to tell exactly where things are. So the first one is on the 2, and notice there's a comma because that's just one of these methyl groups. Then there's the 4 is where the next methyl group is, and then the 4 is where the next methyl group is, and notice there's a dash. Okay, so it's number, comma, number, comma, number, dash, substituent, parent. Okay, so we have this is our prefix, this is our infix, and this is our suffix, the E at the end. So questions on that? Longest possible chain, lowest number for the first substituent, and then locate the substituents correctly in your name. Okay, so that seemed pretty easy in that example, but there are other ways to do it. Once all substituents have been identified in their proper location, you now then alphabetize them, except you don't include prefixes like di, tri, tetra. So in something where you have, let's say you had a methyl group, an ethyl group, and a propyl group, right here, you would actually, when you put these in, you would put the ethyl in the beginning, you'd put the methyl in the middle, and the propyl would come at the end. But you would also add a number, like the methyl is on the 1, the ethyl is on the 2, and the propyl is on the 3, where it would be. So if they are not the same, you still number by the first one given, but you alphabetize the substituents next. Okay. Now note, a hyphen is used to separate the numbers from the letters, and a comma is used to separate that. So if I were to redo this in the correct order, I would have 2 ethyl dash 1 methyl dash 3 propyl. Okay, so dashes separate numbers and from letters, and commas separate numbers from numbers. Now, the prefixes sec and tert are also ignored in the isobut. However, the iso and neo are not. Weird rule. Hopefully we don't have to run into that on an exam, but I think there's one in the homework just to make you think. All right, so we have identified our parent chain. We've identified our first substituent. We have identified that's how we're going to number the chain. And now we know that once we have all of our substituents identified, we reorder them in alphabetical order. Okay, so let's put all those things to use here. Okay, so again, we're going to have 1, 2, 3, 4, 5, 6. We're going to have hexane as our parent chain. Go ahead and practice a few times, making sure, does this have to be 1 and does this have to be 6? No, this could be 1 and this could be 6. It's going to give us the same number and the same substituents. So just make sure that you have the longest chain possible. Okay, and it's not always in a straight line. You will see some that will kind of go around a lot. So always look for that not straight line as well. Okay, so we have 1, 2, 3 substituents identified. So we get to use the methyl because it's a 1 carbon substituent, and we get to use the tri as a prefix because there's 3 of them here. Okay, so again, let's look at where we have it. So if we number this way, we would have our first substituent on 1. Oh no, we have our first substituent on 1 again if we name it from the other direction. Okay, all right, so now we have to go to the next rule on that is this: if the first 2 substituents can't positively identify which side you start the chain on, you have to go to the next lowest substituent. So if we went in this direction here, our substituent would be on 4, but if we went in this direction, our substituent would be on 3. Okay, so we did the first rule where we got to the lowest number for the first substituent, and that was still ambiguous. So we have to go to this next substituent. So that means we have to label it from this side. So we have the lowest numbers of 2, 3, followed by 5. Okay, so that being said, that means our correct name would be 2, 3, 5 dash, tri because there's 3 methyl groups, methyl, hexane. Notice there's no space between the methyl and the hexane. Most of these go continuously straight through. There's very few, only like certain functional names will have a space. But in the hydrocarbons, it's going to be all one word. Okay. All right. So now let's kind of practice and see whether or not we can actually find the correct chain. These are 2 drawings of the exact same compound. And I said that the longest chain is not always in the straight line. So let's try start from, obviously we'll try to start from here. And just as an example, 1, 2, 3, so that can't be it. 4, 5, that can't be it. 6, 7, 8, 9, 10, 9, 10, 9, 10. Oh no, we have 3 possible ends. 1, 2, 3. They would all give us 9 carbons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, I don't know where I got 10. They would all give us 9 carbons. So we have 3 choices. Okay, but there's a rule about that. Okay, the rule about that is because this is a branched right here, we actually, that would only give us a total of 3 substituents. 1, 2, 3. Okay, however, if we were to go instead along, I'm going to use this one, along this chain here, and instead go this way, that would give us a total of 1, 2, 3, 4 substituents. Okay, So you want to choose the longest chain with the greatest number of substituents. And the reason for that is it actually makes it easier to name because you have less branched chains. Okay, so now let's go back and apply all our rules. We have longest chain, which is 1, 2, 3, 4, 5, 6, 7, 8, 9 over here. 9's off the page here. But I numbered it backwards, didn't I? Because if we number from the other direction, from this 9 over here, this is going to be the number 1. Let me change color. This is going to be number 1 if we number it from this side, or oh, there it is. All right. Notice that if we number it from this other side here, this is going to be, if we number it 1, 2, this substituent is now on the number 2. This substituent is on number 3. So that means this is the first substituent we encounter, and it's not ambiguous. We must start on this end here as number 1, number 2, number 3. So let's erase those and draw it correctly. So it's okay to try and then double check your work, make sure you're doing it. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so that'll give us 9, which is nonane. Okay, nonane, 9. And we have one methyl group, we have an ethyl group, we have an ethyl group, and we have a methyl group. Okay, so that means we get to do dimethyl and diethyl. Which one do we put first in our name? Remember, we drop the di, tri, and tetra, and we just look at the substituent itself. Ethyl comes before methyl alphabetically, so we're going to start labeling our ethyls first. Okay, so remember, this position, this number 2, is identifying that functional group as the first substituent, that substituent as the first substituent we encountered. So when we number our ethyl groups, we have 3 ethyl, 6 ethyl. So we're going to have 3, 6 dash diethyl. So that takes care of 2 of the substituents. We have these last 2 methyl groups, and they are on carbons 2 and 7. So we have dash 2, 7 dash. There's a dash missing there. Dimethyl, nonane for the 9 carbons. So we now have an unambiguous name for all of the carbons in this compound. Okay, we know exactly where the methyl groups we know exactly where the ethyl groups are, and we know exactly how long our parent chain is. That's the beauty of following these rules, nomenclature rules, step by step. All right, questions on that? Okay, so the rules we've learned is parent chain, lowest number for the substituent. If it's ambiguous, you need to move to the second substituent. Always look for the longest chain, even if it's not in the straight line. And then once you have identified all the substituents, you have assigned their numbers based on that lowest numbering priority, then you take those substituents with their numbers and start them at the beginning of the name, and then you end it with the parent chain. Okay? So, and then when we add rules to this, we are going to continue on, but we're going to use these same steps each time, and we're just going to add things onto the end of this. I have a question. So you don't name the parent chain till the last on at all, till last. Yes, the parent is the last name, or in fact, technically, what we're going to see is that the functional group is going to be at the end here. And in this case, this E actually turns out to be naming our functional group, but the functional group is what goes at the end here. I'll talk more about that E in a little bit. Okay. So now that was straight chains. Okay. Rings are a little different. And so when you have rings, hydrocarbons in a ring, the molecular formula changes because you're losing 2 hydrogens at the ends of the chains to create a new carbon-carbon bond. So the molecular formula has changed to however many number of carbons there are, twice the number of hydrogens, okay? Now, These, whenever you have these cyclic alkanes, we tend to use the word cyclo plus the number of carbons in the ring. The number of carbons in the ring turns it into the parent, and then you have substituents coming off it. So it's, however, if you have 5 carbons in a ring, it's a penta, cyclopentane. If you have 6 carbons in the ring, cyclohexane. Okay, so it's the number in the ring, not the total number of carbons you have. All right, so let's take a look at that. So when you have names for cyclics, you look at which chain has the longest, has the greatest number of carbons. Okay, and that's the parent. Okay, so notice that here we have 3 carbons in this, but we have 4 carbons on the other side. Those 4 carbons now are the longest chain, and therefore they count as the parent chain, and our cyclic group counts as our substituent. Okay, you don't go, oh, well, 8, 9, 10, 11. It's not that, because you have to identify that cyclic group as separate. So it becomes a substituent if it's smaller than the straight chain. If the cyclic group is bigger than the straight chain is now the substituent. So in this case here, we have, this is 6 carbons, this is 3 carbons, so that means this is now the substituent. And so we have to name it for 3 carbons, which is prop, YL because it's a substituent, and the cyclohexane is the number of carbons in that parent chain, the biggest number of carbons. Can the cyclic group be a substituent? Yes. If the main chain is longer than the number of carbons in the cyclic group, it is a substituent. Okay. Getting some good questions in the chat, by the way. Keep it up. All right, so when we number, numbering can be a little confusing on cyclics. So if you just have 1 substituent on there, that obviously becomes the 1 position because you start from that, okay? So cyclic just means ring. That is true. Okay, when you number alkanes, you're going to number the cyclics. You're going to have the lowest number substituents possible, okay? How do we tell the difference between a ring of 3 carbons and 6 carbons and stuff like that? Well, again, you count all of the carbons that form that ring, and then you use the nomenclature of prop for 3, but for 4, penta for 5, and then you add cyclo to the beginning of it. So that's cyclopropane, etc. And so that's how you name them. Okay. So if we look here, we have a total of 6 carbons on our main chain right here. So that gives us cyclohexane right here. But now we have 3 different substituents. And whenever we have substituents on there, we want to give the lowest possible number to the first one. And if there's a tie, we should also give the lowest to the second one, just like that previous rule, where if they're ambiguous, you name it from both sides, you have to give the first 2 the lowest possible. And in this case, we have 2 methyl groups right here, which means those methyl groups can be assigned as 1 and 1. So we can correctly name this as the 1,1-dimethyl, but the other group is on this 3 carbon, which is a 3-ethyl. Ethyl comes before methyl, therefore it's 3-ethyl-1, 1, dimethyl cyclohexane. Notice it's all one word. Okay. So again, we're using that rule of finding the lowest number first, and if that is ambiguous, you need to find the second substituent and have that also on the lower number. Okay. And if cyclics weren't troublesome enough, when you put 2 of them together, it gets even crazier. Okay, so when you have 2 rings fused together, we now call those bicyclo. And it's not a bicycle, it's bicyclo. Okay, so it's because you have 2 cycles in the ring. And so the thing is, when you have these bicyclo compounds, you actually just add up all of the carbons in both of those rings, and then you put bicycle in front of it. Why is the one carbon on the dimethyl group again? Okay, so there's a question here about why are the methyl groups here. So if we numbered it this way, right here, where the ethyl group is on the 1, then our next one would be on the 3 and then the 3, okay? So we have 1, 3, 3, okay? If we used this as our number 1, we have 1, 1, 3. So we have a net, the second substituent, this one right here, would be on the lowest carbon, the number 1. Here, the second substituent would be on the 3 carbon. So whenever we have that possibility, we actually name it for we go to the other way, so the second substituent's on the lowest number possible. And in this case, it happens to be on the same carbon. Okay? All right, so with bicyclose, it's the total number of carbons in the rings. So 1, 2, 3, 4, 5, 6, 7. And when you first start out with bicyclose, make sure you draw pencil marks on there to make sure you're counting them all. So we have 7 carbons here, so that gives us heptane, but we have 2 rings, so it's bicyclo. Notice this is a flat representation right here, so it's kind of flat and it's kind of showing that there's definitely a carbon here in the middle. However, if we were to tilt that on its side, give it kind of a 3/4 view, this is kind of a 3/4 view of it, showing that it has this little top hat looking thing on it. But they both represent the same compound. Okay, so in bicyclo compounds, we want to talk about a couple different things. And number 1, we have different types of carbons in our thing. We have what we call bridgeheads, and those are the carbons that are creating the bridges to the carbons that are making the linking, okay, the link point, okay? So when we think about that, these carbons right here are basically where the 2 rings are fused together. And these carbons here are what we call bridgeheads. Those are the ones that are linking those different sections. Notice that all 3 bridgeheads attach to the same 2 carbons, okay? So what you're looking for is a tertiary or quaternary carbon to have everything linked to. Okay, so when we name bicyclo compounds, we look for the number of carbons in each bridgehead, excluding the ones they're attached to. Okay, so in here we have 2 carbons on this side, we have 2 carbons on this side, and we only have 1 carbon on this side. Notice that that's only 5 of the 7 carbons. Okay, because the 2 carbons that create the fusing are not used, they're counted in the name, heptane, but not in the location of where the bridges are. Okay. So why do we care about that? Well, by identifying how many carbons are in each bridge, we will know exactly the configuration. So we have to identify them as, okay, 2 carbons here and 2 carbons here and 1 carbon here. Okay. So when we name that, we go bicyclo. Now this is backwards. We go the highest number first, then a dot, then the second highest number, then a dot, then the third highest number. And notice it's in brackets. This is different than substituents where you have a dash or a comma. It's only used in naming bicyclo compounds. So we have a bicyclo, and then we have 2, 2 dot, 1 dot. So that means anytime you do a bicyclo compound, you should be able to say, okay, I'm going to draw my 2 fusing carbons first, and then I have 2 carbons between that, and then 2 carbons between that, and then a 1 carbon over that. And that's how you can build your bicyclo compound just based on your numbering system here. Okay.
I have a quick question.
Yes.
How could you tell that there wasn't, how do I say this? Like 3 bridgeheads, I guess, like in that other intersection on the left between the 2 and 1, like where the triangle is.
Okay. Now, when we're looking at bridgeheads, we are identifying these angles here. This is telling us we have a carbon. We have a carbon here because it's at the end of a point. And so we're actually counting the carbons on those bridges. So we have a carbon here attached to a carbon attached to a carbon. And because these are the fusing ones, we only count the ones that outside of the fuse. Is that answering your question?
Kind of. Okay.
So, I mean, we count all the carbons for the name, and then we count the carbons that are not the fusing carbons as the bridges. Okay.
Okay.
All right. All right. So I'm going to move on. Okay. So now when we name things with bicyclic compounds, we actually try to do the same thing where we name the longest bridgehead first. So we start with one of the fusing carbons, and then we name the longest branch first, the second longest third, and the third longest bridgehead last. Okay, so let's just take a look at this name right here. We have octane, it means we're gonna have a total of 8 carbons. We have a methyl group, so we have a substituent on that 8 carbon bicyclic compound. Okay, so if we were just to look at this name and say 3,2,1 octane, we'd want to draw it where we do 2 fusing carbons, and then let's do 3. 1 carbon, 2 carbon, 3 carbon bridgehead, fuse. Then we have the 2. 1 carbon, 2 carbon fuse. Then we have the 1 carbon between the 2 fuses. And that's how we draw that structure. Okay. So now when we number it, we start at one of those fuse points and name the longest bridge first. So 1, 2, 3, 4, 5. Now we could go up to here or over to here, but we're going to do the second longest bridge second. So that makes this 6 and 7. And even though it's not directly attached, that last carbon becomes our 8th carbon to make our octane. Okay. So now when we look where our substituent is, because we named our longest bridge first, our second longest bridge second, and our third longest bridge last, we end up with our methyl group here is actually on the number 8 carbon. Okay. So you have to name the number the bicyclic compound first in this, and then the substituent is where it is. Okay. So this is one of the weird situations where you don't try to put your substituent on the lowest number. The name of the bicyclic compound determines how it will be numbered. Okay. Questions on that? So bicyclos are a little weird. We have brackets, we have dots. Those are only found in bicyclos. And we number the longest bridge first, and we number all 8 carbons. So those are slightly different rules for the bicyclos. Everything else follows those other rules we were talking about. Okay, let's see, we're at 9 o'clock, moving right along. Okay, questions about alkanes. Okay, longest chain, substituent on the lowest number if possible, second lowest number if necessary. We can have, if we have 3 of the same, we can do tri. If we have 4 of the same, we can do tetra. And then as we name, okay, let's see, I have a question here. On the second image on the left, how could you tell the 2 cyclo and not 3? Oh, why does it look like, okay, that's a question. All right, so if we look at these 2 compounds here, okay, why is it a bicyclo compound and not a tricyclo compound? Because it's like, well, there's this 5-membered ring here and a 5-membered ring here and then a 6-membered ring here. Okay. Now, the reason it's a bicyclo is if we looked at the carbons, we have 1, 2, 3, 4, 5 carbons. We've consumed those carbons. And so we only have this last one to make our second ring. And now we've consumed all our carbons. We would have to have a 4th bridgehead to have a tricyclic compound. So that's why it's bicyclo and not tricyclo. If the cycloalkane only has one substituent, do you ignore the number or is it always one? No, you name the you number the bicyclo compound first. Oh, that's an interesting example. So let's say we have a substituent here, okay? And we know that we have to number it using this system here. So we have to start with our one. Let's start with red here, one here. So because we can number this direction or that direction because they both have 2 in their bridgeheads. So we have to number one of those bridgeheads first. It's the highest number, okay? But because our substituent is here, we actually should number from this one here. So the substituent is at the lowest number, okay? So, however, numbering the largest bridge first is more important. For example, in this one here, if we put our substituent instead of, well, let's just add another substituent on this carbon here, okay? So if we added another substituent on that carbon here, we still have to number around the longest one first. However, if we changed our numbering system from 1, 2, 3, 4, 5, 6, that puts this substituent on the lowest number possible, 7, and this is still 8. So it'll be 6, 8, dimethyl, bicyclo, 3, 2, 1, octane. So that's the only time you would try to renumber the system, but you still have to renumber around the largest bridge first, the second largest bridge second, and the last bridge last. Okay? I think that answers your question. Okay. All right, let's take a break. I'm gonna drink some green tea here. Now let's get on to alkenes. All right, so everything we saw before was alkanes, okay? So alkanes have only carbon-carbon single bonds. There are no pi bonds in there at all, okay? So by changing our system and adding at least one double bond or pi bond, we now have changed the nature of the main chain. So now the parent chain has the suffix -ene on it. So it's A for alkane, E for alkenes, Y for alkynes. Okay, so keep that in mind. Now, because we've taken 2 hydrogens away to make that double bond, our general formula has changed. It's turned closer to what we saw in the cyclic compound, where we have the number of carbons and 2 times that number of hydrogens right here. So that's a good way to kind of identify that. And it'll always have that -ene at the end. Now, the key here is when we're naming our parent chain, the longest continuous chain must include both carbons of the pi bond. Okay, so that means you can have a really long substituent that ends up not being included in the parent name because it doesn't contain both of the carbons in the double bond. All right, so let's explore that. Okay, so because we have to include both of the carbons in the double bond, we have to start where we have, and in general, we like to try to give the alkene the lowest number as well, if at all possible. If we number from here, 1, 2, so we've included both carbons of the alkene first, 3, 4, 5, 6, 7, this would give us 7. And if we go the other way, we get 8. Okay, so that means our longest chain containing both carbons of our double bond is 8. And so we also note that this is, if we number from that direction here, our substituent and our alkene are both at the lowest number. Our alkene starts at this 1 carbon. And notice we only have the 1 there in the name. You do it for the first carbon, where the first carbon is found in that alkene. And I'll do that rule again. And then our substituents on the next lowest carbon, which is 3. So we have 4 carbons, which makes us a butyl group. So we have it on the 3 carbons. So we have 3-butyl, oct-1-ene. Okay. Now, you can write it -1-octene. You can put the 1 in the front here. However, it's more precise to have it oct being the number of carbons, than the 1-ene, showing you exactly where the alkene is. Okay, so it looks a little funny, but it's going to be the more precise way to do it is substituent, number of carbons in the parent chain, and then identifying where the alkene is. Okay, so it's the first carbon in alkene is on that number 1 carbon. All right, so there's different types of alkenes, and that gives rise to how we're going to name them actually, because if you have a monosubstitute or only one alkyl chain hanging off there, it's a monosubstituted group. And the cool thing is that means your alkene is always at the end of the chain. Okay. Now you can have disubstituted in 3 different ways. Okay. You can have them both on the same side, on the same carbon of the double bond. You can have them on 2 different carbons, but notice how the R groups are pointing onto the same side of that double bond. Okay, so we would call that our cis configuration, or on the same side configuration. And then this is our trans configuration, where the R groups are on opposite sides of that double bond. Okay, so we have 3 possibilities for 2 groups attached. Once we get to 3 and 4 groups attached, we only have 1 isomer for each of them. And we need to, when we start finding the parent chain, we actually have to go through this double bond in all of its configurations to figure out where the longest chain is. Okay. So with the idea that we can have these multiple types of alkenes, monosubstituted, disubstituted, trisubstituted, we actually start getting into a little bit of stereochemistry. Okay. Now, stereochemistry just means in space. Okay. Now I said that these are on the same side of the bond, and right here, and these are on opposite sides of the bond. Okay. Now, in a regular hydrocarbon, a sigma bond can rotate. Okay. However, a pi bond can't. Okay. This is that 120-degree trigonal planar structure. It's fixed in space. Okay, that means that this, if you synthesize this where these 2 R groups are on the same side, they will stay on the same side until you change it. Okay, so this is actually stereochemistry. This is fixed in space. You can get a bottle of 100% cis alkene, 100% trans alkene. Okay, so that's an important part. And so when we think about stereoisomers, that's its configuration in space. And cis means same side, trans means opposite sides. Okay, so when we start looking at this, if you have 2 similar groups, that's where you can use the cis and the trans. And you can use that in your name. Okay, so let's take a look at this compound here. We have a total of 4 carbons, but our alkene is not on the number 1 carbon, right? Because we have to name from the end of the chain. So this would be 1, 2, 3, and 4. So we have butene, but we have to identify where the first carbon was on that chain. So that's where we get but2-ene from. Okay, so we have 4 carbons, we have a double bond, and we starts on the number 2 carbon. Now, the next part of it is we actually can tell that the 2 similar groups are on opposite sides of that. So we call that the trans. And notice when it's typed, it's italicized. Okay, when you write it, it doesn't have to be italicized, but you can try. But if they're on the same side, it would be, again, this is just a different isomer. So it's the cis but because there's still 4 carbons, still on the 2 carbon, and still an alkene. Okay. So to identify these as cis and trans, you need to look for the groups being different from each other, okay? So the 2 and the 3 need to be different from the 4 to be able to differentiate that. And when we get into the stereochemistry chapter, we actually have another level of nomenclature we're going to use for that, but I don't want to start that yet. Okay. But just knowing the cis and trans for disubstituted is appropriate for this chapter. Okay. So that being said, we want to look for our cis and trans to be basically the 2 same groups that are opposite each other. Okay. So in this case here, we have an ethyl group, and a methyl group. That methyl group is the different group. So these 2 ethyl groups are cis to each other. So we know that they are also containing the main chain. So we only have 1 substituent. So we have the cis group, the main chain is cis to itself, 3-methyl, 3-ene, hexene. And here we have 2 propyl groups that are the same. And so we can say that those are opposite each other with 2 smaller substituents here, because remember, those smaller substituents mean they're not part of the parent chain. And we can say that that configuration is a trans, and then we have to add our substituents. Notice this substituent is the lowest alphabetical order. So that actually telling us we need to go 1, 2, 3, 4, lowest alphabetical. 5, this is our next one, methyl 4-octene. Okay. Questions on alkenes so far? We have a little bit more to go. A couple more rules. Okay. So now, when we talk about alkenes, if we have more than just hydrocarbon groups on there, we need to be more specific about our stereoisomer terminology. Okay. And so what we say is we have the E and Z terms. Okay. So E means entgegen, which is opposite or trans. Z means zusammen, which means same or same side. Okay. So when we do this, it'll be E opposite, Z same. However, we have to identify the priority of the atoms. So this is assuming we don't have things like carbon in there. And so we have like a carbon, a hydrogen, and other atoms here. So now we have to think about what the priority is on either side of that. So the first thing we need to talk about is when we're assigning E and Z to double bonds, we need to have, keep in mind, a couple different axes. First thing we're gonna do is we're gonna draw an imaginary line down the middle of the double bond, okay? And we're gonna look at one side, the A side here, and then we're gonna look at the B side, okay? So we're gonna take that imaginary thing and we're gonna look at the A side and we're gonna find the highest priority atom on that side and then identify it. Like here, we're gonna draw an asterisk on it and I'll talk about priority. Then we're gonna go to the other side and find the highest assigned priority on the other side. In this case, it's gonna be bromine. And because this is the highest on this side and this is the highest on this side, they're on the same side, okay? Which would make it the Z determination. One thing you can remember is Z zusammen is on the same side. That's the way I remember it. So it's make it easy to remember. Okay, now let's talk about priority. Priority is all about the atomic number of the substituent, okay? So in the case here, let's just talk atomic number. Atomic number hydrogen is 1. Atomic number hydrogen of carbon is 6. Therefore, 6 is higher than 1. It's the higher priority, okay? It's atomic number, not atomic weight. Okay, oxygen is 8 and bromine is like 20 something. So bromine is higher. So it is the higher priority than oxygen. Now, what if we had an OH here? What if we had an oxygen here? Our oxygen is 8. It would have a higher priority. It's all about On this side of the double bond, which is the higher atomic number? On this side of the atomic, which is the higher atomic number? And that's how you assign E and Z. Okay. Now, what if they're look similar? Okay. What if you have two carbons on either side and so they look the same? Well, you have to keep going out further and further and further until there's a difference, until there's a higher number. Okay. So let's use this as an example here. Okay. So on this side, if we split this in half and look at this side, bromine's obviously the higher number, okay, because it's in the 20s, oxygen's 8, so we're done. We just identified that side of the molecule, okay. But we go over here, this is atomic number 6, this is atomic number 6. They're the same. Okay, so we're done, right? We can't identify this? No. Let's find a differentiation. We'll go over here, and this is 6, and this is 6. Okay, that's the same. Okay, now let's go over. Remember, there is a understood hydrogen hanging off here, so that means our next priority number on this side is 1. It has the atomic number 1. However, this has a 6 on it. So that means this now is differentiated from this because it has the next atom over is higher priority. Okay, so let's look at that in a little more detail. So if we draw all our hydrogens there, we end up with this being C with 2 H's and C with 2 H's. So that's the same. We go over one more till we have that higher priority. Okay. Once we have that higher priority, we now have this carbon has only hydrogens on it, but this carbon has another carbon on it. And if that carbon has another carbon on it, that breaks it as the higher atomic number than hydrogen, and that gives it priority. So in this case here, this one has priority, this one has priority. So is it E or Z? Chat room's open. All right, so we're coming up on time. So I want to do a couple of examples of this E and Z to try to get you to, that's correct. All right, everybody's getting. So, and these priorities can look a little different sometimes. So for example, you have a double bond and you have OH, OH, Cl, Cl. Actually, that does not look like Cl. Cl. All right. So we're going to do our system. We're going to cut an imaginary line down the middle and look at one side first, then the other side. Okay. You don't assign all 4 different little things. You only do one side, assign priority, the other side, assign priority, and then you're done. You can assign E and Z. So here we have 6 and 6 because those are both carbons. We have 6 and 8. So that's identified this as the higher priority right here. So here we have 6 and 6, and then this is 35 and this is 6. So now we have differentiation. This is higher. So this has priority. And so what do we assign this compound? Even though it looks almost the same on each side, it's just that one carbon difference is the difference in the priority. So our priority has now changed because they're on opposite sides of there. So it's Ingagen or E. Okay. So that's stereochemistry for alkenes. When we pick up on Thursday, we are going to talk about alkynes. And luckily there's no stereochemistry in alkynes. Okay. Questions on alkenes and or stereochemistry in our last couple of minutes here. Okay. So it's important to use the process, cut in half, look at one side, assign priority, look at the other side, assign priority. Some people try to assign priority to all of them and or accidentally assign priority to this half versus that half. That don't put your line down the middle here. You must have your line cutting the double bond in half. Okay. If you follow that process, you should be able to identify it correctly each time. All right. Well, it's right here at 9:20. I'm going to go ahead and stop recording. And if you want to hang back and ask a couple questions, please do. Okay, there's more.